Okay, in the previous segment, we talked about how to predict the direction of the magnetic force by using the right-hand rule. Now we want to actually calculate the magnitude of the magnetic force. And so, just as a review, let's go back to gravity and also talk about electricity to introduce the concept of the magnetic force. So let's first talk about gravity, where you're going to have mass number 1 and mass number 2 separated by a distance r. So the formula for the force of gravity is it's going to be a fundamental constant of nature called the gravitational constant, and then it's going to be mass number 1, mass number 2, and then separated or divided by r squared. So that's the formula for the force of gravity. Okay, then you have the formula for the force of electricity, Coulomb's law, depends on a fundamental constant of nature, the electrical constant, and then it's going to be charge number 1, charge number 2, and then the whole thing divided by r squared. So notice how similar the two formulas are. So early scientists wanted to know, could you do the same thing with magnets? And so here was their idea. And so they said, let's take a magnet, and let's say that this is the north end of a magnet, south end of a magnet, and then here's another magnet over here, south end of the magnet, north end of the magnet. Let's attach them to a string and bring them close to each other, and then you know that the north end is attracted to the south end, so they'll go together. And so they measured the distance between the two magnets, and they came up with a formula that said that the force of magnetism would be equal to some constant, which they didn't know, but they said it was a magnetic constant, and then it would be pole number 1, and then pole number 2, and then divided by r squared. So they came up with this formula that would go with magnets. Well, it wasn't a very successful formula because it's almost impossible to figure out what's the magnitude of these poles here. So this formula is never, ever, ever used. So let that one drain out of your head. It was a good try, but it didn't work. But then you remember from the previous segment that if you have a current carrying wire and then you put it next to another current carrying wire, then they would be attracted to each other. So let's call this one current number 1, and then this one over here can be current number 2. And so they came up with a formula that said that the force of magnetism was going to be equal to a fundamental constant, so the same K sub m, but then it's going to be current number 1, and it's going to be current number 2, and then divided by r squared. Now this isn't quite an equal sign, so this is a proportional sign. So they came up with a formula that would match with this one here, and it does work. So this is a useful formula if you've got two wires and you want to calculate what the force of attraction or the force of repulsion is. So if one of them is pointing up and the other one's pointing down, then the two wires are repulsive. And you can use the same formula to do it. But the one that I am interested in, though, is the bottom one. Okay, now in this case, so let me erase, let's erase this stuff up here. You can read a book or something while I'm doing this. Okay, so in the bottom picture, you're going to have a magnetic field that is going down, and then you had a charged particle that is going in this direction with the speed v, and then we found out using the right-hand rule that the direction of the force was going to go into the board. So I'll symbolize that with an X for the tail of the force. So it's going into the board, and I'll just say that that is the magnetic force. So all three of them were perpendicular to each other. And so they came up with a formula that says that the force of magnetism was going to be equal to the magnitude of the electric charge, Q, times its speed, and then times the magnetic field. So this is the one that I would like for you to know for the exam. So you don't need to know about this one. You should know that if you got wires that are pointing up, they will be attracted, and if they're like this, they're going to repel. So that's what I want you to know. But don't worry about the formula on the exam. So this is a formula you should know. Let's compare it to, over here, electricity. So if you have an electric field that is pointing down, and then you take your charged particle, Q, and you put it into that field, it experiences a force of electricity that's going to pull it down. So again, notice how it's not the same as this one over here. The force and the electric field point in the same direction, but over here they're perpendicular. But look at the formula. So the force of electricity is going to be equal to Q, just like this one. It's going to depend on the electric field, like this one over here, but this one doesn't have the V. So this one does depend on the speed. So let's assume first that the particle is not moving. So if the particle is initially not moving, what would happen? 0 times anything is 0. So if this charge is not moving, it's just going to stay there. It's not going to do anything. So you do have to have a charge that is moving in order for it to experience the magnetic field. So let's do a word problem that you should be able to do on the exam. So what force does a 5 Coulomb charge traveling at 8 meters per second in a 2 Tesla magnetic field experience? So we're given 5 coulombs. Coulombs is the unit of charge, so that's Q. We're given 8 meters per second. Meters per second is speed, so that's the V. We're given 2 Tesla. Tesla is a unit of magnetism, so that's the B, and we need to solve it for F. So we take our numbers, we put it into our formula here, we solve it, we get the number 80, and then we remember that the unit for force is the Newton, so we stick an N on there. So it's going to be 80 newtons. So that's how you can calculate the magnitude of the magnetic force. All right, so when we come back, we are going to discuss magnetic materials.